had some decisions to make when I was preparing this talk, and I decided that I will give a lot of introduction. So half of this room consists of young people who I don't know, which probably means that they don't know what homotopy is. So my apologies to the experts in the room. I will, yeah. All right. So with that, those apologies made. So I will to the words Picard group and the K local category in the title, and I will define those words. So we'll start with a symmetric monoidal category. An object in the category is invertible if there exists another object such that this product gives you back the unit of your category. And then the Picard group consists of isomorphism classes of invertible objects. All right. Now, well, so here's a basic example. Let's take the category of spectra. Then, okay, well, let's take the suspension of the sphere spectrum. That has an inverse given by another suspension of the sphere spectrum, so that's equal to the sphere. And turns out that's all. So the Picard group of the category of spectra is just the integers generated by the suspension of the sphere. All right. The Picard group becomes much more interesting when we localize the category of spectra. And I'm going to tell you a little bit about how we do this. It's going to be a very quick introduction to chromatic homotopy theory. All right. So I guess the reason why we're here is that we want to understand the homotopy groups of spheres. So I don't know how much you know about this. Well, I guess half of you know a lot, half of you don't. This is really hard. Okay. So we need to do things to it. All right. Now, in algebra, when people have some complicated ring or module that they're trying to understand, it often helps to localize that ring or module with respect to prime ideals. Localize with respect to some ideals. So in topology, we can do something similar. We can localize our categories. And we localize with respect to carefully chosen homology theories. With respect to homology theories. Some homology theories give you better localizations. Some homology theories give you localizations which come with nice computational tools. Maybe Agnes told me you don't have to do this, but I will. So for every homology theory, I'm just going to give it a quick definition. For every homology theory E and spectrum X, LEX is the part of X. So X is a spectrum. LEX is localization of that spectrum with respect to E. So this localization is the part of X that E can see. Okay, so in particular, if we have another spectrum A and the E star of A is 0, then there are no maps from that A to localization of X with respect to E. All right. So one example is given by the P localization. So that's the construction that allows you to think about your stable homotopy one prime at a time. Okay, so from a spectrum, it picks out the part that knows about the P torsion, or rather the part that does not know about any other torsions. So the P localization of X has the property that this property, that every other torsion is thrown away. All right. All right. So then, I guess the second example. So we're going to fix a prime P. In fact, the experts probably choose a prime P before they start talking about mathematics. So we fix a prime P. And then we start doing things. Okay? So after you fix the prime P, there is a sequence of, remember I said carefully chosen homology theories? Well, so there's a sequence of carefully chosen homology theories called Morava K theories. Take note if I can. Okay. So what are some properties? Well, I don't know if I'll need this, but I'll write this down. So that's the coefficient ring. See how there is no P in the notation for the Morava K theory? It's very confusing. But P is chosen in your head. And the second property is that Morava K theories are complex orientable and have formal group laws. Oh, maybe I should write this down. Formal group law, gamma n of height n. So these Morava K theories have something to do with the formal group laws, and we're going to, this formal group law is going to come up again in 5 minutes. All right, so before that, so why are these theories useful? Because if you choose to localize at the product of the first n of them, so I'm going to denote this localization by ln, then there's some trick to this, right? So I guess I have to put this down first. Then do this. Right, so we denoted by ln the localization function with respect to the wedge of the first n plus 1 Morava K theories. And then by construction, there are maps like this, which form something called chromatic tower. And this chromatic tower converges to X. Well, not for all X, but for X you're interested in. So for X, which are finite, P local. Remember, there's P chosen? So that's P local X. And this is the chromatic convergence theorem due to Mike Hopkins and Doug. All right. Okay. So these Moravsky theories are useful because they let you break your spectrum into smaller pieces and then recover it back as a limit. All right. So there's another theorem. We're going to break our spectrum once again. So these pieces fit into homotopy pullback diagram. All right, and so which tells you, maybe I should write it down. Which tells you that you can compute these localizations if you know these. So these are the building blocks of the pre-local spectra. And I should put names here. So when I was a fifth year grad student, and I was preparing to give my talks, and I asked Paul who this theorem is due to. He said, well, it appears first in Hodge Strickland, so I put his name here. And then he said, it's probably due to Ravenel because everything is. So, is there some other names? Mike, I don't know, the other names here? Bausel? Yeah, I feel like, yeah, all right, well, any names you would like to put there. All right, so we're interested in these building blocks, and that's why there's a K2 local in the title. Oh, did I do the blackboards the wrong way again? I did, right? Okay. All right, next time. All right, where are we? Right. So these localizations are computational tools. The tools come from the formal group laws. So if you have remember there's this gamma n, the formal group law of height n, that comes with Moravsky theory. So you can define what morphisms between formal group laws are, and in particular, you can define what automorphisms are. And these automorphisms form a group, which we denote by Sn, and call Morales stabilizer group. And then, so there is this FPN. Whenever there is an FPN, there is a Galois group. So this GN is also called Morales stabilizer group, or big Morales stabilizer group. Now, how is this all related to spectra? All right, so this is a big theorem. I'm not saying that these people wrote one big paper. That probably would be nice if they actually wrote a book. But anyway, so this is a theorem that is a meta theorem combined of different theorems. Daniel Davis. And yes, did I forget someone? All right, so fix the prime P. Then there exists an infinite ring spectrum. En, called Moravsky theory. I will tell you what the coefficients are. I don't know if I'll need it. The coefficients are, well, the bit vectors on fp to the n. Then n-1 many power series generators, and then a polynomial invertible polynomial generator. This lives in the graded degree 0, and the degree of u is -2. Okay, so there exists a spectrum, and which comes with an action of Gn, that Gn, acts on En where infinity maps. If there is a group acting on something, then you can take fixed points. In this case, you take homotopy fixed points. And after we took these fixed points, that is identified with the Kn local sphere. Okay, so that's great. So we wrote the Kn local sphere as fixed points of some action of some horrible group on a spectrum. And then, so we get an extra 2 because of that. There is a spectral sequence whose EG page is the cohomology of this group acting on En, and it converges to the homotopy groups of the fixed points, which remember is equal to homotopy groups of this. And also, for a closed subgroup of Gn, we can fix, which we can build that exists. Fixed points of En under the action of those subgroups, and there is again a spectral sequence, which computes for us the homotopy of that. All right, now, so Gn is a profinite group, so the correct thing to say here is a continuous cohomology. Here also, if the H is not finite, then it's continuous cohomology. If H is finite, then this is just regular cohomology, which still might be extremely hard to compute. But so these spectra are sometimes relatively easy to understand. It's easier than this, for example. All right. So should I put some more names in the theorem? I hope people who are involved don't mind being in one theorem together. All right. Any questions? Well, next time. Next conference. All right. So, okay, what should I do? Should I put this down? Yeah. All right. So now, so I'm doing topology, but I'm doing this algebraic topology. So in topology, we're dealing with Kn local spectra. Okay, so a Kn local X, and it's algebraic. So the algebraic gadget that describes a Kn local spectrum is this, which you have to be careful what this is. This is the homotopy groups of Kn localization of En smash X. So En is a Kn local spectrum. X is also. The smash product might not be Kn local, so you have to relocalize and then take homotopy groups. Okay. And this, I'm going to use this later. This is called Morava module of X. And this is a spectrum which is, oh, sorry, this is a module which is rich. It has an action of En star and Gn, and they're compatible with each other. All right, so now I should probably talk about the Picard group. Okay. So the Picard group of the Kn local category is much richer than the group of spectra, which is just Z. So, and we're going to denote it, so let's denote it by Picn. All right. All right, and then, so here's the first theorem. A Kn local spectrum is invertible if and only if its algebraic thing is invertible. Okay? So if and only if its Morel module is an invertible Morel module. Which is equivalent to En star Z being a free rank 1 En star module. All right, so the first thing that you need to understand when you're thinking about the Kn local Picard group is what are the invertible Morel modules, right? That is called the algebraic Kn local Picard group. It consists of the modules such that M is En star. So En is, is it still there? En, no, it's not there anymore. En is too periodic. So if M is a rank 1 En star module, there's two options. M could be En star or En star plus 1. So it could be shifted by 1, because if you shift it by 2, you get En star back. Okay, so epsilon is 0 or 1. All right. So I'm just going to do a little several bureaucratic steps in order to get to where I need to get. So here they are. So we can construct a map, which takes a module and goes to epsilon. And then the kernel of this, I'm going to denote big N of 0, and that consists of modules which are actually isomorphic to En star. All right. Then I can take peak N and do the same reduction and derive peak N0. And then the last step that I need to do, tilt on the next black part. So now I'm going to map peak N0 to peak N alg 0. And if you lost, that's fine, because this is the important part. So now I'm going to, so please wake up. I'm going to take the kernel of this map and going to denote it by kappa n. And so that consists of spectra such that their Morava module is equal to the Morava module of the sphere spectrum. Okay? So this is called the exotic part of the Picard group. And this is I guess this is the part I'm going to talk about. Okay, so let's look at this and think about it. So these are the spectra such that algebra thinks that they are sphere. That the spectra in Kn are spheres. Because if you compute the Morava module, it's Morava module of the sphere. Yes. No, in general we don't. Do we even know that n equals 2 and prime 2? What was Hans-Werner's? Yeah, no. Yes. Yeah. I mean, invertible things form a group because you can multiply them with each other. It's a category. People say yes, so. Anyone else? All right, so, okay, so algebra thinks that these are spheres, and we need topology to distinguish them. Okay, so this is the part where we need topology. All right, so how are we going to use topology? So let me give you one sort of one demonstration of how topology could be used. Maybe here? No. Sorry. There. I'm inverting Kn equivalences. Is that right, roughly? Does that help? Okay. So that he would know more, he would know more. All right. Okay, so I promised to tell you how we use topology to distinguish spectra. Okay, so remember there's a spectral sequence, which is gone. So there's a spectral sequence which as an input has cohomology of Gn acting on En star and converges to homotopy groups of this. Okay, now so Z has Morava module which is equivalent to that. To En star itself. Oh, did I stop writing? Not yet. All right. So because the Morava modules are equivalent, we get an equivalence of cohomology groups. And now I didn't tell you this, but this spectral sequence would converge to homotopy groups of Z. Let's see some of the E2 pages. Okay, and so this, the E2 page, and their equivalence is algebra. But these two things are not equivalent in general. And so what distinguishes them is topology, which happens here. Topology is in differentials. And so in starting with the same, so the different elements of the exotic Picard group have the same E2 page of this descent spectral sequence, but the differentials might be different for different elements, and that's topology. All right. So we're going to use that and some other things in our proofs. That's not our only method. All right. So what's the other way that we have to distinguish different elements of Kn? Oh, kappa n. So here's another one. How? Great. So this can be rewritten as an equivalence between spectra. So see, En thinks that Z is a sphere. So En smashed with Z is the same thing as En smashed with a sphere. Okay? But the sphere, the Kn local sphere, the unit of the category, definitely does not think that Z is a sphere. It thinks that Z is Z, which is not equal to ENHGN. Okay. All right, and see, I left empty space here because, so this is the biggest subgroup of Morava stabilizer group. There are others. Let's take various subgroups of Morava stabilizer group and see whether this equals to ENH, H1 or not. And then you can keep doing this for carefully chosen subgroups. And sort of that gives you a hold on their elements from kappa and some hold. All right, maybe this is the time to introduce the notation. I'm going to call kappa n H, so H is a subgroup. It consists of spectra Z such that ENHH still thinks that Z is a sphere. Okay, so when the subgroup gets big enough, it's harder to fool the spectrum. So yeah, anyway. All right, so what do we actually know about things? Doesn't distinguish Z from the sphere. No. Okay, so let's see. So this is fixed under the action of the trivial group, right? En is that. And so kappa and trivial group is hold the kappa. I think that's right. Yeah. All right. So what do we know? Sorry, there's an arrow here which goes down, so that'll be later. Example. Let's do an example. Right. So let's take n equals 1 and prime 2. All right. So let me tell you some things. So G1, the Morava stabilizer group at 1 and prime 2, is the units in the 2-adics, which is isomorphic to this. And this is the maximal unit subgroup. Okay. So suppose we have a Q that lives in couplet 1. Then, well, E1 slash Q has to be E1. But, so how about we take the fixed points of E1 under the action of this maximal finite subgroup? Well, that's a spectrum. It's related to the real K theory. It is in particular aperiodic. Okay, so we could use it as a test object to test the Q, and turns out there exists a Q. So there exists a Q in the kappa 1 such that this is suspension 4 E1HC2, and suspension 4 E1HC2 is not equal to suspension 8, and in particular it's not equal to E1HC2. Okay, So this tells us that Q is not a sphere. It's a non-trivial element of couple 1. Also, because 4 plus 4 is 8, we know that Q squared is trivial. Well, we don't know that, but that's a suggestion that Q squared is trivial. And turns out that's all. So couple 1 at prime 2 is Z mod 2 generated by a certain Q. Yes. So Q is a K1 localization, because we are in a K1 local category, of a finite complex that looks like this. All right. So at least sometimes the exotic Picard group is known. So what else is known? At other primes, couple 1 is 0. And it's, as I said, it's Z mod 2 at prime 2. Don't have a reference. Is that Hopkins, Mahovol, Sadowski? Is that right? Kappa 2 is 0 if prime is bigger than 3. Z mod 3 times Z mod 3 if prime is 3. And order 2 to the 9 if prime is 2. Okay. And, okay, so what are the names? So this is Goers, Hen, Mahovol, and Risk. This is us. Karmanov and these people? Okay. But, oh, Karmanov was prime 3, okay. All right. And something else is known. It's known, see, there's a pattern here. I start with zeros. Kappa n is 0 if p is large. And we don't know what it is if p is small. Not large, yeah. Okay, which plug right now? This one? So I guess now I should move on to n equals 2 and prime 2. And now I will stop writing en and start writing e for e2 because there will be no other n's. All right, so, oh, still here, great. Remember I was saying something about smashing with some things which are fixed under the action of a particularly carefully chosen subgroup. So, actually, I'll leave that here for now. All right, so what are the carefully chosen subgroups at n equals 2 and prime 2? Let's see. So the Morava stabilizer group decomposes as, I don't want to say more. These are elements of norm. There's something called norm in the Morava stabilizer for the elements of the Morava stabilizer group, and these are elements of norm 1. That's why there's a 1 here, and these are different norms that they could have. No. Okay, I guess I'll say more. Okay, so the norm goes to Z2 cross. No, wait, what? I'll get it. It goes to Z2 cross, which then identified with Z2 mod C2. And the kernel that So how do we do this better? Let's do it this way. Is that better? So it's C2. Yeah, I'll talk about this. Yeah. All right. Okay, so we're gonna need this subgroup. Oh, maybe this is the place to say its property. So this is almost K-local sphere. It differs by the Galois group. S2 differs from G2 by the Galois group, which is C2 in this case. So this is almost the K-local sphere. And there is a fiber sequence like this. So these things are almost halves of the K-local. Well, this thing, which happens twice, is almost half of the K-local sphere. So that's why, that's why we choose this group. It's important. It sees a lot. It sees a half. Okay? And another subgroup that we need is the maximal finite subgroup. So 2. So maximal finite subgroup of S2 is it has order 24, and we denote it by G24. It has a name. Doug taught me once. It's binary tetrahedral group. Anyway, okay. So that's all. Yeah. Okay. Now I'm ready to state the theorem. So that's sort of expansion on that order 2 to the 9. There is a filtration of kappa 2 at prime 2. Like this. Where we know the successive quotients. Okay, so this quotient is this is Z mod 8. The next one is Z mod 2. And then the last guy is Z mod 4 and Z mod 8. Okay, so this is 2 to the 3. So 3 plus 1 plus 2 plus 3 is 9. Yeah. So that's why there's a 2 to the 9 here. All right. So I'm going to use this space. Maybe I won't. Okay. So I want to elaborate a little on these. Okay. So what does the Z mod 8 mean? Okay. That means that there exists an element in kappa 2. It is an exotic element such that P smash EHG24 is suspension 24, EHG24. So the kappa 2 G24 does not distinguish these P's from the sphere, but that's why the quotient would. Okay, so this 24 is important because EHG24 is 24 times 8 periodic. And this 8 is this 8. All right, so now, is that still here? Yes. So this role of this P is analogous to the role of this Q at prime 2 and 1. So C2 was the maximal finite subgroup, here G24 is the maximum finite subgroup. So that Q, as Doug asked and I answered, that Q is a K1 localization of a finite complex. And so when we started working on this, I spent a painful year of my life trying to construct this P as a localization of a finite complex. So I had some notes of Mahovald where he outlined ideas for how it could be constructed. It would be a complex with 24 cells. My collaborators did not like to talk to me about this. When I drew this, it looked insane. So I didn't fully give up hope. I have an A2 module that might or might not do this. I don't have an A module, so I can't realize it yet. But it might or might not have 1600 of A2 modules, of A module structures, because A2 has 1600 A module structures. So I don't know, maybe later. At some point, Agnes showed up and proved that P exists as a not a localization of finite complex, but okay, so what's the idea here? So we can look, so I guess this is now for the experts, and I don't have time to define what these things are. Okay, so the Gross-Hopkins dual of EHD24 is suspension 22 EHD24. And Spania-White dual of EHD24 is suspension 44 EHD24. And the difference between them is 22, which is not quite 24, but it's maybe we can tell you about the details about it later. So using these two effects, you can prove that P exists, that it exists a P which does this. All right. So what else did I want to tell you? Okay, so what does this mean? This means that there exists a spectrum. I'm going to call it Q. It's different from that Q. It's just Q is the next letter after P. So Q. There exists a Q such that Q smash EH G24 is EH G24. So they're different from these. The EH24 does not distinguish, but EHS21 does. All right. And what does this mean? Well, that means there are some spectra such that half of the sphere of the K2 local sphere does not distinguish them from spheres, but the whole sphere does. So Z is not equal to K2. Yes. Oh, yeah. So the eraser is there. Is there another one? Yeah, that's a good idea. Thank you. Or up? Oh, down is better, I think. All right. Oh, great. All right. So what did we use for this and for that? So we used the finite resolutions of K2 local sphere and related spectra. So maybe that could be a theorem. That there exists a resolution in the K2 local category of this spectrum So this is your friend EHD24. C6 is a subgroup of G24, so this is subgroup of that. And then this is a spectrum fixed on direction of C6. Okay, this resolution gives you a spectral sequence. So as the resolution is not very exciting, what's exciting is the spectral sequence, which has as input homotopy groups of the terms. So do you have space? Okay. And they're shifted homotopy groups of 2.4, and another 2.4 at the bottom. And it converges to the homotopy of the spectrum that we're resolving. All right. So this is nice because these spectra are, I wouldn't say they're easy. This one is 192 periodic. This is 48. But we know these homotopy groups, and so at least we know this E. This is an E1 page. At least we know this E1 page, and in particular, we can compute pi 0 with EHS to 1. And you see, how did we get this Z mod 4 times Z mod 8? Well, that's a part of pi 0, which lives in none of my Ruka filtrations bigger or equal to 1. Okay. So this is Z mod 4 times Z mod 8. And so it's when you do I have that? Don't. Okay. So you see what lives in this group are spectra such that this half of the sphere does not distinguish them from the sphere. Okay? So something happens when you put things together into this fiber sequence. Something happens in here that knows that Z is not a sphere. So we get back, I guess, this. And that something that happens is related to this pi 0. So this upper part of pi 0 gives you the ways to twist this map to obtain, to realize differences. Okay, so I guess I told you something about this, something about this. Now, the Qs. The Qs also come with the help of this resolution because, so Qs are spectra such that these finite subgroups don't know about them. So if we smash everything here with a Q, the terms are the same, but the maps change. And then, so these maps change, and so your limit is different. So the limit is going to be this, which then you have to double up to get that Q. Right? I guess I can stop here. Of a finite complex. Do you know anything about exclusion disease? Oh no, and there was not even hope really. Yeah, I mean, we just so we hoped for P because we were guided by the example of n equals 1 of that question mark complex. So because there was one, we hoped that there might be one here, but for those others, we didn't even think about it. Yes. Sure. But see, I don't have an eraser. Okay. Okay. Wait, this is yellow. Okay, so I of EHT 24 is suspension 22. D is suspension 44. All right, and now there is this relationship. Oh, I shouldn't have written that there. I should have written. Well, anyway, there is this relationship between the two kinds of duals. Okay, so sorry. Now I'm going to sort of rewrite this again. Suspension 22, suspension 44, and this. So this is the K2 local Brown common dual, and of the sphere, and it's suspension 2 as that, which I have to define, smashed with, okay, give me a letter, B, where we know that B is in the K2, in the kappa 2. Okay? Okay, now let's smash everybody and equalize and subtract. Yeah, so that 44, okay, I'm going to erase this now. 44 becomes a minus 44, so a minus 22. And this 2, I'm going to erase that 2, becomes a minus 24. As that smashed with EHT 24 is EHT 24. And so we just showed that there is a B in kappa 2, so there's a B smashed with that, is suspension minus 24.